All right, welcome back, everyone. Um, we are going to continue talking about uh, the stuff for quiz three, like the kind of the third half of the class or third part of the class. So today we're going to talk about. So we're going to switch gear. We're going to talk about the new thing, uh, which is about multi-core systems. So where are we now? If you remember at the beginning of the class, I showed you this picture and said that, okay, initially we managed to do a lot of things to make the computers faster. And this was kind of like, the major part of the computer architecture and how computer architecture contributed to making things fast. And all of the things that we discussed so far was kind of like belong to this era. So out of order execution, branch prediction, pipelining, forwarding, all those great ideas happens during this era. And early 2000, like 1990s and so on, that was like computer architecture was one of the hottest topics in computer science in general. So there was like packed, classes. I remember my one of my older professors was saying that computer architecture class was like packed because everybody wanted to do things, like learn about those things because that was like the golden era that we brought microprocessors and we could build like laptops, and then later on that leads to also building cell phones and all that. So these are all thanks to this kind of the golden era of computer architecture. But then kind of like things dipped a little bit because essentially we managed to pack all the things that we could have packed, right? So we talked about a lot of optimizations, and we kind of figured most things out. And if you remember at like around 2004, we had this thing called Powerwall, which was Intel put so much things into so much features into the processor, make it so large, super scalar, lots of functional units and stuff like that, that the power consumption of the chip was so high that the temperature was no longer manageable. So the amount of heat that the processor was generating was so large that we couldn't actually pack more things to it. We couldn't like increase the super scalar, issue width and things like that. And that was when that we kind of like the rates kind of somewhat slowed down. But what helped us to kind of increase the trend and make things still faster was the idea of the multi-core. Okay. So multi-core is when you're transitioning from the uniprocessor to what we call the multiprocessor system. So in a uniprocessor, we have this context of concept of threads. Again, for those of you who took any course in operating systems, you're probably familiar with the concept of threads and process. But generally, I'm not going to go into the details of the differences, but generally think about thread as something that has the following context: it has the PC and has the registers, okay? And it has some form of a stack, okay? So that you can have local variables and all that. So when we have a multi-thread system, we can actually switch between these threads. So we can change the PC, we can change the registers, we can change the stack. We can also have some shared states between the threads. So usually some global or heap or and so on could be also shared between multiple threads. Uh, uh, but generally, this is kind of like what we are assuming that we have. And then we have a process, which is kind of like a bigger thing than the thread. And usually a process has its own memory space, and then it has its stack, code section, heap, and so on and so forth. And then in order to be able to run multiple applications, we kind of switch between these threads. And this is usually the role of the scheduler, or in most cases, an operating system. Okay. And then threads is not a new concept. Threads has been around for quite some time. Operating system has been around for quite some time. Like Windows has its own, the The biggest, one of the biggest innovations again in 90s was bringing like things like operating systems such as the Windows 95 and so on. But up until 2004, most of these systems was uniprocessors, which means that all the threads were all running on the single core. So we had this thing which is called context switching, that we had to kind of like run one thread for some time, or run one process with multiple threads for some time, then switch to another process and run it for some time, and so on and so forth. This will give us the illusion of concurrent execution. So if we can switch these things fast enough, you will not be able to realize that these are not actually concurrent. But there is also a limit to it, right? So at some point you will realize that these things are not as fast as you want. Okay. And this is what we usually refer to as thread level parallelism. So what is that? Remember a long time ago, we talked about instruction level parallelism, ILP, and we said that essentially by having superscalar processors, we can feed multiple instructions into the pipeline so we can run things concurrently, right? And then the limitations of that was data dependency between instructions and poor branch prediction and the memory latency. So like regardless of what we do, we're always limited by some memory latency. And then we also introduced the notion of out-of-order execution, and we showed that out-of-order executions can, again, solve some of these problems, but it's not like out-of-order magically can fix all of these problems. And then in the project, you have seen things like this, which if you have, let's say, 4 different functional units, you may not be able to always utilize all the functional units at all time, depending on dependencies, the size of your reservation stations, if you need to flush things and so on. So there could be sometimes that some of these functional units are empty. So what you would hope that, for example, to achieve like an IPC of 4, you may not get it in real world, right? So your instruction per cycle is usually much less than that, right? So what we can do to fix this problem, and as I said, we can interleave programs and introduce the concept of thread level parallelism. There's nothing that prevents us to run 2 threads at the same time if we have the capabilities in hardware, right? So for example, this is one program, and this is a completely separate program. So for example, imagine in your CA3, your simulator can read the GCC trace and the hammer trace at the same time, right? What will happen is that your decoding logic gets a little bit more complicated, but then what you can do is that you can interleave this into your functional units to utilize the execution much more, right? So to make sure that FUs are always busy, because dependencies of one has nothing to do with the dependency of the others. You need a copy of your register file and all that, but you can do that. This is actually the idea of what we call simultaneous multi-threading, or SMT. This is also called hyper-threading by some different companies call it differently, but typically it's referred to as SMT. The idea of SMT is that you can execute multiple programs, in other words, multiple threads on the same pipeline. So you can actually like fetch one instruction for program 1, fetch another instruction for program 2, and feed both of them to your functional units. Nothing prevents you from doing that. Okay. And then you can actually have fine grain and coarse grain simultaneous multi-threadings that I'm going to actually show you in a bit. So how do we actually implement SMT? We need kind of duplicate, similar way that we had, superscalar processing for a single for for a pipeline processor, we made it multi superscalar. The same thing now is that we can think about this as adding another dimension to this. So initially, for example, we said that, okay, we have one PC, but instead of reading one instruction, for example, we read 4 instructions at a time, right? So that was kind of like superscalar. That's what you implemented in your CA as well. But now what we are saying is that let's actually add a dimension in this direction, and let's add another 4 instruction from a separate part of the memory. So I need a different PC, but also feed that 4 instructions into the pipeline as well. So I can, instead of like having an 8 with pipeline, I have still 8 instructions being fetched, but 4 of them from one program, 4 of them from another program. Okay. And now I have the PC. I also need to have separate register file, because register 1 for program 1 is completely different than register 1 from program 2. These are 2 separate programs. So I need different register file. If there requires address translation, I need like page tables and all that for address translation. If there are things like exception handling that we're going to talk about later, we need that. But you don't need necessarily to duplicate things like ROB or reservation station. You just need more entries, but you don't need to like separate them. You can always tag them by like program 1 or program 2. You can tag them by thread IDs and so on and so forth. Okay. So as I said, your data path would look like something like you have one PC here, one PC here. Then you have, instruction memory that takes 2 addresses, like address 1 and address 2. And then you have a bunch of instructions from one thread and bunch of other instructions for another thread. So this would be your instruction memory, right? And then you can have your decode logic, for example, that decodes these instructions all at the same time. So you can have 8 instructions kind of coming out of the decode. And the rest of it, honestly, would be basically the same for all of them. The only separate thing is that you have a register file for one of them and another register file for another one. So everything would be tagged based on the thread ID or program ID. So some of them will access this register file, some of them will access this register file. Everything else would be kind of similar to what we have. So what we're trying to do is just further duplicating and making the processor bigger in order to be able to run multiple programs at the same time. And again, this could be just a superscalar. For the difference between an SMT and superscalar is that in SMT, instructions are from different programs versus our superscalars are all from the same program. Okay? And then one thing to remember is that multitasking and context switching is a different concept than SMT. SMT means that I run things at the same time simultaneously. But multitasking or context switching means that I run one of them for some time, then I switch and run the other one. So at any given point inside my pipeline, there's only one set of instructions from one program. It's not like, both at the same time. And of course, you usually need to spend some time to save the state of the previous program and to load the state of the new program. So usually operating system does things like it stores the program counters, registers, a stack pointer, etc., etc. So it has like usually a separate memory for this. And then it loads the program counter, register, stack pointer for the other program, and then it continues. So that will be the job of the operating system. So this will work, and as I said, this is originally what we had, but what we want to do now is, can I somewhat run this in parallel together? Any questions so far? Okay, yeah.
Wait, but like, can you still have multiple threads if you're doing that or focusing on a single thread machine?
Yeah, so actually this goes into this question. So this thing. So we have normal execution, a CMT or coarse grain multi-threading, FMT or fine-grained multi-threading, and then SMT, which is simultaneous multi-threading. So what are the differences? So in the normal case, let's say I have a 4-wide processor that has, like, let's say 4 functional units, okay? In a conventional processor, the way it works is like the following, that you run one thread, let's say green, for some time, let's say like for 6 cycles. Then you want to run another program, so you spend some time to context switch. Context switch itself is some activity, so it requires a bunch of computation. And then at this point, you start running the next thread. And again, this is a superscalar processor, so you can run 4 different things. Blocks here means that which of these functional units I'm using. For example, this one in this cycle is used 2 of them. In this cycle, I only use 1 of them. In this cycle, I use 3 of them, and so on and so forth. Okay, so this is a conventional. Then we can have what we call a coarse-grained multi-threading. Coarse-grained multi-threading usually happens when you can context switch between them very quickly. And this is typically achievable by doing the context switching directly in hardware. So you can like copy things or have the copy of PC inside the hardware. So you don't need to like copy things like back and forth using the operating system. You can instantly switch between them, okay? So the difference between this guy and this one is that here I no longer need to spend this many cycles to context switch. I can quickly change things. This would require more storage in terms of register file and all that. But for example, let's say I reach into like a big cache miss. I realize that, it's a page fault or a cache miss. I need to spend many cycles waiting for this data. Instead of wasting the cycles, I can quickly switch to another process, okay? So this is actually called CMT. Then I can go even crazier than that and switch it every cycle. So if this is a hardware that is capable of doing that, I can actually switch at every cycle if I want to, okay? This is usually called fine-grained multi-threading. And finally, the SMT is when I have a superscalar and I don't care which instruction is for which. I can actually feed them all at the same time into my pipeline. So if I, for example, look at the snapshot of my pipeline, I'll see that, for example, in one cycle, there might be 2 instructions from the green thread, 2 instructions from the red thread. In the next cycle, I see 1 green, 1 yellow, 1 blue, and so on and so forth. There's usually limits on how many instructions can I like simultaneously execute. But as you can see, if I just compare the number of cycles and the number of actual functional units that being used, you see that the most utilized one, of course, is the simultaneous multi-threading one. But of course, this is also very, very complex in terms of implementation. Did I answer your question? Any other questions here? Yeah. Fine grain allows you to kind of switch between the threads at any cycle. So usually the coarse grain waits for some events to happen and then switch. But the fine grain gives you the flexibility of switching at any cycles that you want.
What's the state of the art?
The state of the art design is the SMT, so it's a simultaneous multi-threading. No, simultaneous multi-threading is the state of the art. Yeah. Although, I mean, SMT also has disadvantages because it's a nightmare for security purposes, because you're essentially saying that applications can literally share same physical hardware at the same time. So now imagine one of these applications is trying to kind of do some form of an attack or trying to extract some information from the other. So in many of the commercial cloud servers, simultaneous multi-threading is actually turned off. All right, so this is still, as I said, for a single processor. Okay, so this is still uniprocessor. It's superscalar, and it's multi-threaded. Okay, so the natural extension of this is, can we actually leverage multiple of these cores? And then either extend the threads into multiple cores. So if I have, let's say, 8 different applications that for some reason I want to run them all at the same time, I run 4 of them in one core and the other 4 on the other core, right? And that gives me significantly more bandwidth in order to run things at the same time. But even more importantly, if I have some applications that are written such that it can be parallelized, right? So think about like graph applications, think about matrix multiplications and so on. Then I can actually spawn multiple threads and then run the threads in parallel together. I'm actually going to give you an example of how does that work. Okay, so for the multi-core, the big thing is how do we first like design such a system and architect such a system so that we can leverage the multiple cores. The design choices and the majority of our time today is going to be to talk about important challenges that multi-core brings and we need to fix. Okay. Um, this is kind of like a funny image that you would think. So this is kind of like, you think that, okay, multi-core gives you the image on the left. In reality, though, things are very messy, right? So it's not going to be that, oh, everybody just takes their share and they run it and then they kind of like synchronize. There are lots of things that can go wrong. So that's an important thing to remember. Another thing that I want to also talk about is the differences between different class of processors, kind of also answering your question. So having multi-core or SMT is not like a standard in all across different group of processors. So typically PCs have a 4 to 8 core systems. You typically don't see like large systems. They're usually 4 to 8 wide processors. They are usually out of order. They typically have SMT. They have 3 levels of cache and so on and so forth. For server, we are talking about significantly larger number of cores. So for example, Intel Xeon or AMD's, different version of the AMD has like a server grade processors that ranging between like 32, 64 cores. Um, and then they have SMT. They usually like still 4 to 8 wide, superscalar, and out of order. And then if you go to the embedded domain like ARM, Cortex, M, or A series, they're usually like either single core. In some rare cases, there are 4 cores. So for example, the Raspberry Pi, if you're using it, this is actually a quad core system. So it actually has 4 cores. But like a lower systems, the smaller systems typically have just 1 core. Or maybe they have like a one M series core and A series cores next to each other. They usually in order. Typically, they don't have an OS or they have limited OS. Typically, they don't have virtual memory and so on and so forth. Another thing that you probably have seen and heard is the code names. NVIDIA has code names. Intel has code names. So like Skylake versus Broadwell versus Haswell versus Comet Lake and so on and so forth. So if you heard these names, this is just about the generation of the processor that they have. The differences between generations is typically most of all, it's the technology. So for example, whether it's a 14 nanometer, 10 nanometer, 7 nanometer, and so on and so forth. And the second thing is that if they actually add new computer architecture features, so maybe they have a better branch predictor or they have a different prefetching algorithms and so on and so forth. That's their difference as well. Same thing for NVIDIA's like Grace Hopper or Blackwell and so on and so forth. So these are the differences. All right. So let's talk about multi-core. So now the idea is that I want to be able to run multiple threads at the same time on multiple physically different cores. Each core is the same thing that you have seen before. It's a superscalar. It can support simultaneous multi-threading, but now I'm also extending the number of cores. So I run 4 of these at the same time. Okay. Um, so the fundamental question that comes into the mind is, okay, how do we connect this to the memory, right? And typically the connection to the memory looks something like this, that we have the cores, we have what we call an interconnect or substrate, and then connected to the memory. The reason that we have to do it this way is that each core are big in terms of the size, the silicon area that they need. They need lots of heat sink capabilities in order to extract the heat and dissipate the heat. So they cannot all be integrated into the single silicon wafer. Okay, so we typically have, like, if you look at this, the pictures of these cores is that you have these cores like next to each other on one wafer, and then you have connections on the motherboard, and then you have like something like your RAM that has, like, multiple different of these what we call like chips, and this is like your core, and this is your DRAM, right? And then you can buy like slots of DRAM and put it into your motherboard, and this thing is called interconnect. The important thing is that distance and the electrical capabilities of the interconnect is really, really important. So, talking among themselves inside the core is really, really fast because we are talking about micrometers, nanometer distances. But if for example, this thing wants to talk to the main memory, it needs to go millimeter or tens of millimeters in order to actually reach to the DRAM. And it also needs to go through lots of capacitance and lots of inductance to actually, talk to the memory. And again, these are all means delays. So talking to the memory, generally going through this interconnect, is not really, really fast. There are lots of research going on how to make this interconnect faster and nicer. And that's actually a very hot topic at the moment, given that we want to big, like, massive systems that can run like LLMs and so on. But generally, just keep that in mind. Yes. Yeah, so interconnect is unfortunately a must. We cannot integrate everything into one silicon chip. We don't have the space for it. Yeah, so that's what I'm saying. So you cannot like interconnect, you cannot like integrate a memory next to a core on the same silicon wafer. It's not possible because the core itself is big and the size of silicon is small. So each silicon area, like each chip, is small, and you already, like, make it as big as possible because remember I told you that we hit the power wall, so we cannot make any chip bigger. So that's why you need to go through kind of the PCB board through the motherboard in order to reach to the memory system. Yeah. Say it again. Yeah, DRAM is also a semiconductor, of course. It's a different technology for building it, but it's like it's still. Yeah, it's a silicon. Yeah, yeah. DRAM it is. Flash and all is like different materials sometimes. Yeah.
So it's something that each course
So that's actually the question that we're gonna get to, which is like, where should we put the cache? Short answer is some of the cache will be very close to the core. Some of the cache will be closer to the memory. So, and that's actually, remember I told you that, L1 is 1 cycle, but L3 is for like 100 cycles. And I mainly told you that this is because of the size, but reality is not just the size, it's also because of going through this interconnect. Okay. Before talking about that, let's actually talk about how multi-core helps. And as I said before, there are two reasons that multi-core helps really a lot in our modern systems. One is multitasking. So if I have different applications and I want to run them at the same time, if I only had one core, the only option was like doing some form of a SMT. And if I have more applications and the number of things that I can do SMT, then I also had to do context switching, right? So I have to run like program A, B, C, and D, let's say, for some time. And then maybe I need to context switch and do, let's say, E, B, I don't know, C, and F, and so on and so forth. So I need to kind of constantly switching between these applications, which means that there will be times that one of these applications won't be running, right? Versus if I have multiple cores, then I can do like A, B, C, and D in one core, and then E and F in another core, and then move on. So everything will be truly parallel, right? So that's one thing that we can have. And as I said, most of the like real systems that we have somewhere between 4 to 8 cores. That's because usually that's the amount of applications that you really want to run in parallel, because as I said, most of them can also support multi-threading. So you don't need to, like, you can technically have like, up to like 16 different apps running at the same time, which is kind of like the limit that you can think about of the number of things that you want to do. Okay. But as I said, the bigger motivation for multi-core is thread level parallelism. That if I can somehow take one application and make it parallelized so that it can independently run on different cores, then I essentially get speed up, right? So remember I told you that, when we have one instruction and run 4 instructions, we can technically like increase the IPC by 4, right? So 4 times the IPC if I have singles, uh, uh, single instructions pipeline processor versus a 4 wide processor. Now, if I have, let's say, 2 of these cores and I somehow can run this 4 times, then I can, again, 2 times the IPC, I can increase it by having what we call the thread level parallelism, right? So that's the goal that we are trying to achieve. Of course, this will be limited by the Amdahl's law. If you remember, a long time ago, we talked about Amdahl's law, and we said that essentially the runtime at some point will be limited by the part that I cannot parallelize, right? So it's not like I can parallelize everything. I can parallelize part of the program as much as I can, but then I will be limited by the part that I cannot parallelize. So for example, if I need to read lots of inputs and then make decisions on the inputs, the reading input part doesn't matter how many cores I have. I will be limited by that. Yes, sir. Multitasking and thread level parallelism? Yeah, multitasking means that there are 2 separate programs. So multiple different programs, I try to run them at the same time. Thread level parallelism is the same program. So let's say, for example, I want to do matrix multiplication. Okay. So if I can do the matrix multiplication by just separate all the elements and run off each of these elements on a separate thread, then I'll get thread level parallelism.
One program that
Yeah. Yeah, doing multiple threads, same task, multiple threads. Yeah. Yes.
another portion.
Yes.
Whereas on thread level, the Google Chrome instance.
Yes. Yes. So like you have the Google Chrome versus like a game you play, or like the other, like your email app or whatever, and this is like your multitasking versus thread level parallelism is making one program run in parallel and faster. Okay. And as I said, you can have, this is kind of like, example of how you can multitask, right? So greens are for one program, reds are from another program, and so on and so forth. For multitasking, there are a whole bunch of things, such as how do you schedule, what are the power versus performance, different systems and heterogeneous systems, how do you actually decide what to offload where. Again, if you take a course on operating system, you'll see a lot of this. Like what is the fair way of scheduling things given the resources and all that. We're not going to talk about this in this class. What we are going to talk about is how to generally provide the substrate, the hardware substrate to allow this to happen. The management level of things, of like what task and should be run at which core and so on, that's a separate course. There is also usually a nice course on writing parallel programs. So parallel programming, like knowing about things like MPI, CUDA, pthreads, there's usually a course on this that you can learn how to take an existing algorithm and parallelize it so you can run it on multiple things at the same time. Have any of you taken courses? You did? You had a question? So you took a course. Yeah, I think we do have something here on like distributed computing that talks a little bit about CUDA. Yes. Yeah. Yeah. So there is a bit. I actually do recommend to, if you're interested in these topics, to consider taking it. It has lots of things that we are discussing relevant to that, and generally parallel programming is a hot topic because of the GPUs and all. So learning a little bit of CUDA is usually a good thing to know at this time and age. So what we're gonna focus right now, though, is how to make a single program faster, right? So we're not gonna talk about the scheduling and multitasking, but what we're gonna talk about is a single program. We're trying to parallelize it into multiple threads and the challenges that arises as a result of this thread level parallelism. We're gonna talk about that for the rest of this lecture, okay? Let me also give you like a simple example for how the thread level parallelism works. Let's say I want to do the following. I want to do the sum of 64,000 numbers. So I just want to add them all together, okay? And let's say I have 64 processors, 64 different cores, okay? And for now, just assume that each core just runs one thread, so we don't have SMT and all that. So we usually the very simple thing, and as I said, like if you take courses in this, it will talk all about how do you create these algorithms, what is scatter, what is gather, what are good complexity for these things and all. But for example, if I want to do like a simple thing like summing these numbers on 64 processors, here's the piece of code that I will write, okay? So I'll write very simple code like this. I create this like sum partial, the partial sum equal to 0. Then what I'm going to do is that I'm going to basically say that I write this for, and I use this variable processor number, that this processor number, each processor knows this number. So we start from processor 0 all the way to processor 63. And all of them will run exactly this code. And then as you can see, the processor 0, if Pn is equal to 0, what will happen is that you will start from I equal to 0 and go all the way to I equal to less than 1,000, right? And then you do the partial sum of sum 0. S0 would be AI, which is I from 0 to 1,000. So that would be basically what you will run in processor 0. In processor 1, you will do this, right? So it would be 1,000 to 1,000, to less than 2,000. And then sum 1 would be 1,000 all the way to again, AI, which is starting from 1,000, right? And since these are independent numbers, I can run them on parallel, right? So there's nothing that prevents me to spawn 64 cores, assign these numbers, assuming that I have a way to scatter the numbers to these cores. And then finally, I have a way to gather this number. So I need to basically collect all these 64 partial sums, and someone needs to be able to add them together. But if I look at the way that this works, the most time-consuming part, which is like adding these 1,000 numbers, can happen in parallel. So in other words, in kind of best case scenario, I can do this in 1,000 iterations and I'm done, right? There will be like a 64 to scatter them, 64 to gather them, but the majority is that 1,000 iterations to add this together, right? So this is how we do it. And again, there are ways there are lots of algorithms of how do you distribute this data, like divide and conquer, trees, and so on and so forth, which again, you might have seen it in some of your courses. Yes. So for this example, I don't distinguish between threads and processors. So one thread per processor. Well, the number of processors is usually a hardware limits that you have. So if you buy a really big processor, like a system, so if you have access to like a supercomputer that has thousands of processors, yes, of course you can do this. The limit would be Amdahl's law if you're asking that question. So remember, Amdahl's law was basically saying that you have like the serial part and the parallel part. You can make the parallel part n times faster, so you reduce it by a factor of n, but eventually you're going to be limited by this serial part. So for example, in this case, if scattering and gathering numbers takes X amount of time, the best you can do is that 2X, right? That's all you can do. Yeah. Yes, you can run multiple threads per processor. You can do all like context switching. You can have multiple threads per processor and all that. Mhm. Yeah.
This case with context switching, because they're all like they're just adding some simple switch that you wasted time switching, but you're still just cutting.
You can context switch, but this is designed such that you don't context switch, right? So in this, it's like one go, everything will be summed all together. Someone just needs to gather the partial sums, add them together, and that's it. You have the numbers. So you don't need, this is designed such that assuming that you have enough number of cores, you don't need to context switch anymore. So that's why this is technically 64 times faster than running it in one core. Okay. So what are the key things for thread level parallelism? First of all, it's very difficult to extract. So this one was very straightforward example, but in many algorithms that you write, extracting like independent kernels that you can then nicely distribute it to different programs is not an easy thing. In fact, a lot of people doing work and research on how do we actually write a programs that are parallelizable. And this is actually very important aspects of any systems. In biology, for example, for RNA sequencing, this is an important algorithm. People are doing that on forecasting, in basic science and physics and chemistry. And there are many applications. And again, the one that is like everyone is working on is matrix multiplication because that's a fundamental of any sort of AI applications. But in many cases, both writing parallel programs and then actually extracting the real parallelism is very hard. Even harder than that is debugging these codes. I don't know how many of you have written any MPI or pthread or CUDA programs. Was it easy to debug? No, right? It's much more difficult. The reason for it is that you have these threads running at the same time, and they have no way of like necessarily synchronizing. So not only you might have bugs in one code, now imagine that you have 8 different threads running at the same time. So now you have to reason about the timings of these things. So it's always like race conditions and all that. Yes, sir. The question is, the race condition also applies when you're writing GPU and CUDA. Yes, it can. If you run the program such that it's like running at the same time in parallel, then you might have race conditions there too. Yeah. Another very important part of thread level parallelism is communication overhead. And as I said, the sequential parts. And again, there are lots of research on that space as well. Okay. The bottom line is that n cores won't give you n times faster. So the reality is kind of like this, that you have a system with many cores and you kind of always bottleneck with one of the cores. So also keep that in mind. All right. How do we make it better? We use better algorithms. We use faster communication, parallel programming. And I'm going to like leave it at here. This would be a separate course, as I said. If you're interested, take a, try to like either read some books or take some courses on that. Okay. But what I'm going to talk about now is that if I have a thread level parallelism system, if I have same program, multiple threads running on different cores, as a computer architect, what should I care about and what should I be worried about? Okay. And this is going to be two major things. One is what we call a memory consistency issue, and the second one is memory coherency issues. Okay. So what are they, and why we are worried about them? So important thing is now that I have thread level parallelism, I'm interacting with the memory from different points. And I need to share memory between these threads. Otherwise, there is no point of parallelism, right? If each one is doing their own thing and they don't talk to each other, then there is no parallelism, right? So they need to share, but they are physically separate from each other, from different cores, okay? Um, so now the question is, how should we do this sharing? Where should we put our caches? What algorithms should we use for our caches? And what are the problems that comes out of this? We usually go with like two ways of designing caches for a multi-core system like this that requires sharing data. The option number one is we have one big shared cache, and since it's big, we put it after the interconnect. Okay, so we have the cores, we have the interconnect, and we have a one big shared cache. The second option is we do what we call private cache, right? Which we have smaller individual caches next to each core that is like very quickly can talk to the core, but they cannot talk to each other, or they're not sharing anything. If they want to share anything, they have to go through the interconnect or through the main memory. Okay. So let's actually look into the three main things that we learned so far about caches. Remember, we had the average access time, which was the hit time, miss rate, and miss penalty. And let's actually see the difference between a private cache system and a shared cache system and see which one is better. So for hit time, if you have a private cache versus the shared cache, which one has better design? Like it has a faster hit time. Yeah. Yeah, private cache definitely is faster than the shared cache because private cache, as I said, doesn't need to go through the interconnect. It's very close to the CPU, so you can actually talk to it very quickly. Okay. What about miss rate? And for miss rate, consider two scenarios. Consider a cache-friendly applications. Like all the applications are cache-friendly. That they're like they have small size and they actually use locality and all that. And also think about streaming applications that has large workloads. They don't necessarily use locality. So for cache friendly, which one do you think is better, private or shared, in terms of miss rate? Yeah. Private you think is better for miss rate. Why? Okay, so private is worse, shared is better. Why? Again, because the same reason that fully associative was better than direct map, because in direct map you had like a specific space and you couldn't utilize the entire space, versus in fully associative you could utilize the entire space. Same story here. In shared, you have a shared space. Whoever wants more or less, they can grab it if they want to. Of course, this has a downside for streaming applications. For streaming applications, in fact, private is better because private allows at least a few of the applications who are cache friendly to still benefit from the cache. But those that are streaming, they cannot like impact others, right? Think about like, one of these cores really wants to hug the entire cache. So everybody else will be suffering from that. Versus in private, even if this one wants more, it cannot grow bigger than something that it's already assigned to. So these guys still can maintain some level of quality, right? Versus in this case, if this one wants to hug, it hugs it gets the entire cache, and no one else can use it. And if it's not a cache-friendly application, this one is suffering. All the other ones are also suffering from the sharing the cache. So sharing is also pretty tricky. So you have to be careful about the sharing the cache. when you have different applications. Okay. And what about miss penalty? Yeah. Is better in the shared. Miss penalty, and why? Yeah, you can assume that, for example, like, for this particular case, since the shared cache is already close to the main memory and already past the interconnect, this might be faster. In reality, though, is usually there's another interconnect here as well. And in that case, it's not a big difference between them, especially from the CPU's perspective, the time it takes to go and grab it is the same. But yeah, you can also argue that in some cases, shared is better than the private. Okay? But what about sharing? Which one is much better for sharing? The shared cache, obviously, right? Because essentially you have, in this one, you may need to, like, if this one wants the data from this one, it needs to go through this process. Versus here, you already have that. So you can instantly grab the data. Yes? Interconnect is literally like it's a bunch of wires. So it could be, there are different, like it could be a ring, it could be a crossbar. There are different ways. Like you probably heard like PCIe, right? CXL. These are usually the protocols for these interconnects. Okay. Once we see something like this, that, oh, there is one that is better than the other one, that is like in some cases this one is better, some cases the other one is better, the instant things that come to mind is that why don't we do a hybrid approach, right? Hybrid approach means that since we already have multiple levels of cache, let's do the following. Make the L1 cache private and make the L2 or last level cache shared, okay? And this way, things that needs to be shared will go here. Things that remains private stays here, right? And this way I'll have best of both worlds because my hit time is not really impacted for L1 hits. For L2 hits, of course, my hit time goes down. But then I have better sharings and I can actually benefit from the sharing and goodness of sharing and so on. So this is typically what's been used in all the modern systems, that L1 is usually private and L2 and L3 are usually shared. Okay, so that's typically the gold standard in any multi-core system. Okay. All right. So yeah, so we have the hybrid, and that's all we care about. But then there is actually two major challenges. Okay, and this is what we're going to talk about in the rest of the lecture. Given that we have private caches, but we want to also share data, so we have both private and shared caches and shared data. If we don't properly manage the copies in each of these caches, this will lead into correctness issues. And this is what we call a coherency problem. That's going to actually give you an example in the next few slides. Second thing is that if you don't properly manage the shared cache, we're also going to run into performance issues. If we don't do a proper replacement policy, if we don't do a proper sharing and assigning the sets and weights to different programs, we're going to also run into performance issues and service quality issues. We're not going to talk about the second problem. This would be kind of like, if you take a more advanced computer architecture course, it's going to be talking about that. But we're going to talk about the first problem, okay? And as I said, if we end up in incorrect copies in each of these private caches, we call this a cache coherency problem, okay? Let's have a quick break. We're gonna come back and we're gonna talk specifically about cache coherency problem. All right, so let's see what is this coherency problem. No. Come on. Sorry about that. Okay, finally. All right, let's say I have 4 different cores, okay, and I have a private L1 cache and a shared LLC cache, okay. Let's say I have one single memory address Z. Z could be any number. Let's say 200. Doesn't matter. And let's say originally it's equal to 0. Okay. And let's say, for example, x5 is equal to 10 or whatever. Okay. So imagine that core 0 and core 1, or I think in this example, core 1 and core 1 and core 2 are trying to access this Z address. And these are shared. Again, remember, all of these things I'm saying is for a multi-thread program that is allowed to share the lines, memory addresses. If you have 2 independent programs that are not allowed to share memory addresses, and that is enforced by address translation through the page table. So we still have that isolation mechanism that we spoke about last time, and we have to maintain that. These are actually do need to share because this is part of the same thing. So think about like your partial sum is actually stored in that Z address. Okay? So let's say, for example, we are doing something like, the following, that we initially read Z by core 1 and core 0. So address Z is stored somewhere in the memory, right? So somewhere here Z is stored and Z is 0. When we are loading, we usually load it into L1. So at this point, Z is loaded here and is equal to 0. Address core number 1 is here and is equal to 0, address Z. And then here is also read and is equal to 0, right? So these 2 loads read these 2 values. And let's say later on in the program, core number 1 decides to write to Z, write the value of x5 to Z, okay? So what it does is that it looks into the cache, and remember that we had, for example, the write back strategy, that it says basically that if the data is inside the cache, then what you can do is that you can just update this and later inform the memory system. So what we do is we're going to basically update and say that, okay, address Z now equal to 10 for core number 1, okay? And here's the problem that we're going to face in this instruction. If core number 2 try to read Z, then if we don't properly implement this, it's very likely that core number 2 search through its own private cache and see that Z is already cached and read the value that is cached there. In this case, this value is 0. But in reality, this value should have been 10 because this is a multi-core program, and we are assuming that this write should be observable by all the cores because this is the same address, the same memory. Everything should be able to read and write and read the most updated value of each of the memories. Again, if we don't do this, then we cannot have like a proper and correct code execution in a multi-thread system. So what will happen is that the coherency problem is the following, that the copy that we have for Z here and here are not coherent. In other words, they're not the same because at some point during this process, one of the cores updates without notifying the other processor or the other cache that this value has been updated. Yes? Uh, are we sharing what?
Why is sharing the same? Like, why is shared? I thought it was two different.
Yeah, again, so you have 2 options, like there are 2 possibilities. If there are 2 different programs, then you don't care. You have your own program, you have your own memory space. This one has its own memory space. They live happily together, right? But what I'm saying is we are talking about a program that is multi-threaded. Remember the sum example. I want the sum to be shared. And if one updating the sum, the other one should immediately see it. Yeah, these are two different threads and running on two different cores. Okay. So this is the partial sum example that part of it is running core number 1, part of it is running on core number 2. Okay. Any questions about coherency problem? Great. On top of the coherency problem, we have another problem called memory consistency problem. Memory consistency problem is not about the same address, but it's about two different addresses, but it's about the ordering of those two different addresses, okay? So imagine a scenario like this, okay? So imagine that in core number 1, I have an address Z and an address Y, okay? And then imagine in core number 2, we also have address Y and address Z, okay? Let's say X8 and X7 are like values for X8 and X7 is 200. And let's say originally Z and Y are equal to 0, okay? The memory consistency problem saying that if I run this program, I should always get the same value for X1 and X2. If I'm getting different values for X1 and X2, then I either need to be able to realize the possibilities of this and then do some other things like putting barriers and all that we're going to discuss later, or just change the program such that it doesn't have this kind of different behavior. So particularly if you look in this example, the question is, what are the possible values for X1 and X2 that I can see? And now imagine that any ordering of this is possible. Can you give me a possible values of X1 and X2 in this example? Yeah. Uh-huh.
Reach the small word first, so that like memory of address E already changed to 100, which is max 8. So our next one will essentially just get the value.
Okay, can you so give me like a two values for X1, like one of these scenarios that you mentioned, just one of them, give me the values of X1 and X.
What's just the original like value?
So it could be 0 and 0, right? So simple case that if I run this first and then run this and maybe run this and then run this, then I get 0, 0, right? Any other possibility? So you said that it could be also that I run this two first and then these two first. In that case, I get X1 equal to 100 and X2 equal to 0, right? Any other possibility? Yeah. Yeah, it could be any ordering is possible. I'm not putting any limitations. So what is the other possibility? Yeah. X2 is equal to 200 and X1 is equal to 0. And then how is this possible? If we do it this way, right? So if you run this two first and then run this two, right? Any other possibility? Can we get 100 and 200? Who thinks that we can get 100 and 200? Welcome to the consistency problem. We technically can get 100 and 200. The way that it could work is that, remember we told you about load store and reordering of load stores within each core. And we said that if these two addresses are independent from each other, we want to do speculative loads, right? So imagine that I have like a system like this. It's definitely possible that I run this first and then run this second within that core, because if Y and Z are independent addresses, which in fact they are, I can reorder these things as much as I want, right, within that core. I can also reorder these things from the other core for the same reason that I reorder things on the other core. And if I don't have any methods for synchronizing and announcing this globally, then it's totally possible that stores happens first and loads happens next. Again, what we discussed in the past was we said that here this is not, if they are dependent to each other, it's not possible because reorder buffer will basically flush that, right? But between these two cores, there is no mechanism of checking, right? So if I do this before this, I don't know there are other dependent loads somewhere else that are supposed to be before some other stores, okay? So if we don't know, if we don't somehow speak to each other, it's possible that this program also gets 100 and 200, okay? And this is called the memory consistency issue, that the orderings of read and writes, if they're not synchronized globally, it might lead into some unknown answers that we haven't anticipated. Yes? That's a great point, that this race condition is also stems from the fact that this is a bad code and it actually has inherent race condition that should be fixed. And that is true. But generally, memory consistency problem is not like a software thing or a hardware thing. It's a general problem that you can fix it either in software or in the hardware. But more importantly, the point that I'm trying to make here is optimizations that you make in hardware makes the consistency problem even more challenging, because if I didn't have the reordering between load and stores within my core, I may not have that final answer. Yeah.
I just want to show the people is because we have all of the execution in each core, but we don't have a global check and stuff for all of them.
Exactly. So we have out of order execution within each core. We don't have the global checking of out of order execution between the groups. And then on top of that, this code inherently has race conditions, which results into these other three scenarios. So there are two things happening at the same time. Okay? All right, so this is the two things that we're going to focus on, the coherency problem and consistency problem. For now, I'm going to just focus on the coherency problem and talk about how to fix the coherency problem. In the next lecture, we're going to talk a little bit about consistency problem. As one of the students mentioned, most of the consistency problems are fixed at software. So it's not really computer architect's job to fix that. But we're going to talk a little bit about things that we can put at the architecture level to fix the consistency problem as well. Okay? All right. So revisiting this, the problem that we have for coherency was that I have local copies in my private cache. I update my local copy, but I don't notify others about this update. As a result, others have the old copy and I have a new copy. As a result, we are supposed to access the same address, but we are working on two different values. And that's the problem with coherence. Okay? First of all, coherency can easily be solved if everything was shared. If we didn't have private caches, we could have saved the coherency problem and call it a day. In fact, one of the key ways to fix the coherency problem is using DRAM directory, because DRAM ultimately is shared. So if I keep track of everything at DRAM level, I won't have a coherency problem. But the challenge is we really need our private caches for performance reasons. So we need to deal with the coherency problem some other way rather than just sharing everything and not doing any, not being worried about private caches. Okay? So just keep that in mind that you always can fix the coherency problem just by having only shared caches. Okay? All right. So we kind of formally define a cache coherency under these three things. We generally see that a memory subsystem is coherent if we have these three things. One is read what is written. That means that if a read of X happens on P1, returns a value, should be written by the most writes on P1 if no other course has written in between. Okay. So if I have core P1, okay, and I have my private value X here, and I have P2, I should be able to read this value correctly if no one else is writing to that X. So I should get the coherent and correct value of X from my private cache, and generally from the memory systems. It could be private cache, could be shared cache, it could be DRAM. If no one else is writing to it, I should be able to read this correct. Okay? But the important thing is actually here and here. And this is again the most important challenge in cache coherency. The number two is basically says that the coherent writes might happen eventually, which means that if P1 writes to X and P2 reads X after a sufficient time, and this sufficient time is important, it might not be instantly, but after some time, and there are no writes in between, so that like the most recent write is from P1, then P2 should be able to read the value written by P1, right? That's what's important to have in a cache coherent system. And the third is causality of write, which means that if P1 writes to X and P2 write to X to the same locations, and these writes are serialized, they should see the same order of the writes. Okay, so if P1 writes first and P2 writes second, both cores should understand that P1 was first and P2 was second. If the order is different, then the system will not be coherent. Okay? Any questions from these three things? Perfect. So now the first question that comes to mind, okay, how do we solve it? How do we actually achieve a memory coherency systems? The first thing is that can we actually fix this in software? Can I write good programs that doesn't have the cache coherency problem? And the answer to that is no, because again, this is something that is not visible by the programmer. Caching and what is stored in the cache and what is not stored in the cache is not a visible property of software. So you have no idea when you're reading X whether this is stored in the private cache or whether it's stored in the shared cache, is in the L1 or L2 and so on. So that's not possible to achieve from the software. Maybe it is if you actually make things not cacheable. Okay? So if I have an instruction in the ISA that flush things out of the cache, then I can fix the coherency problem, right? If I make sure that nothing is stored in the private cache, then I don't have the coherency problem, right? If I make sure that Z is never stored in the private cache, or whenever I write it, I purge it from the cache, then I have a coherent system. So to some extent, software can help. And in fact, many ISAs do have capabilities of flushing things out of the cache if necessary. But usually this is not the most efficient in terms of the performance, because again, you're losing the capability of your private cache, which has the fastest hit time. So you don't want to lose that as well. Okay? So there are special instructions that, flush things out of the cache line. Very inefficient. Okay? Same thing with OS. OS can also manage cache coherency. It can detect writes. It can move things around. But again, OS is a little bit slow if you are reading and writing very quickly, okay? So technically, you can have a coherent systems under this assumptions with an OS, but this sufficient time is really long, okay? So just keep that in mind. All right, so then what is the solution? The solution is having what we call a cache coherency protocol, which usually implemented in hardware. The basic idea of cache coherency protocol is like a see something, say something kind of situation. That if we see a write, we announce it to everyone. If you want to flush something from the cache, we tell everyone, and so on and so forth. Okay? And as I said, we use hardware to track this because hardware is really, really fast and allows us to be able to do this in nanoseconds and milliseconds. The trade-off, though, is that if you put things in hardware, the cost of the hardware, area, power consumption, and so on and so forth goes higher. But for high-end systems that you really need speed, you want to actually implement this in hardware. So how do we actually do this? We use this technique called snooping, okay? So essentially, we snoop the cache and the bus between the private and the core and the private and the interconnect. And then if any activity happens, then we do some actions, okay? We're going to talk about a specific protocol called MI, or later we're going to talk about MSI, and then later we're going to introduce ME, O, and F. So at the highest, we have this thing called MOESIF. What it is, what it means, we're going to later talk about it. But essentially, the idea is that if I see some activity, I'm going to basically announce it and broadcast it to everyone and make sure that everyone knows of what's happening. Okay? That's generally the idea of coherency. At the simplest level, we only have two different states, the modified states and the invalidate states. Essentially, the idea is the following, that if someone writes to that line, I announce that write to everyone, and everyone will invalidate the copies that they have. If I only implement this, I will have a cache coherent protocol, right? So going back to the example that we had before, right? So all I need to do for a cache coherency protocol is that the moment I write here, if I announce to everyone that, oh, look, this value is being updated, your copies are no longer valid and invalidated, remove it from your cache, then I'm good to go, right? So next time I'm reading this, I actually can read it back from the memory subsystem and I have the correct copy. Given the fact that I updated the memory and all that. Yes. Yeah. So if I have multiple levels, this snooping happens in all levels. So again, if the cache is already shared, I don't need to be worried about coherency. So this applies to single private levels of cache. So if L1 is private, then you apply it to L1. If L1 and L2 is private, you apply it to both and so on. Okay? Yeah. Yes, exactly. Yes, that's a very valid thing. So if we are writing and we only updating our local copy, and when we are invalidating the others, we also need to figure out what is the right way to read things. And that's actually kind of like, as I said, at the lowest level, you just need to invalidate. But later on, you're going to see like shared and owner and forwarder and all those things to make sure that things are performant and also correct. But you're right. For now, you can assume that we have the write-through strategy, which is if someone writes to their own cache, they also update the mem. Okay? Okay, so here's how basically this would work. So we are essentially have the quote unquote memory bus, and anyone who wants to write to the memory needs to announce announce things to this memory bus. Even if it's a local write, it needs to be announced to this local bus, and then this local bus will snoop and listen to all of these transactions and then broadcast it and tell everyone else about it as well. Okay, so that if, for example, CPU1 is writing address, updating address Z, the snooper listens to this, see that, and tells everyone else that address Z is being updated. Okay, and now what will happen is that all the other caches, all the other CPUs will look through their cache, and if they have the address Z, they will invalidate it. They will remove it from their cache. Okay, that's the simplest thing that we can do in order to achieve cache coherence. Rest of it is just how we make this optimized so that the performance is really good. But this is all it takes to make sure that this cache is coherent. Does that make sense? Any questions? Okay. So where do we store kind of like the information about what is invalidated, what is modified, and things like that? This goes into the metadata of the cache. So remember we had like dirty bits, and we kind of like keep track of dirty bits. We can also keep track of this invalidation validations into that bits as well. So each line of the cache has a unique structure, extra storage for keeping track of this different states of the cache coherency if need be. Okay? So here's what happens. In a simple, as I said, in a simple thing, if if you want to write something to the cache, I invalidate all the lines in the cache and then write my value to it. Okay. If I want to read something from the cache, okay, here's how we actually make sure that the system is correct. If I need to read, let's say, read address Z, and this is actually answering to your question, I will first announce that I want to read address Z, and all the other caches look into their own cache to see if they have address Z or not. If any of the caches have address Z and this address is dirty, then what will happen is that that core is responsible to first write back that value to the memory, and then we're going to read it from the memory. Okay? If nobody has that line and that line is not dirty, then we directly read it from the memory. Okay? So two possibilities. If I want to write, I announce it to everyone. Everyone will invalidate. I write to the line that I want to write. Okay? If I want to read, I announce it to everyone. If someone has that data and that data is indeed dirty, they have to write it back to the memory first. So we make sure that the memory is the most updated value. Then I read it from the memory. Okay? If I have a write-through strategy, of course, I don't have the dirty bits, so I don't need to be worried about. But even if I don't have the write-through strategy, this will ensure that I always read it from the memory, and the memory has the most recent copy. Yes, sir. If you have local copies in different caches and all of them are dirty, yeah, it's not possible. Because when I want to write, I will announce it to everyone else, and they have to invalidate themselves. So the dirty is only exclusive. It's only in one of the caches. It's not possible. If the other one wants to write, it will announce, and this one will invalidate. So the modified line is only in one of the caches. It cannot be possible to be on all the caches. Yeah, so it will always ensure that it's always one of them that has the modified line. Okay? And that will fix the problem, right? So essentially what will happen is that this one reads Z, this one reads Z, right? And for now, they can actually have the copies together or not. This depends on the protocol, and we're going to see it in a bit. But then once this one wants to write, it will announce it, and this one will invalidate the line. Now this one has the updated line. Let's show it with Z prime. Next time that this line wants to read it, it will also again announce it to everyone. And now since this one has a dirty copy, it will write it back to the memory. So now it's Z, and then this one read it from here, and again we're gonna have, okay, so there will be this kind of like back and forth between the cores. They talk to each other, they write back to the memory if need be, and then read it from the memory if needed. Okay? So the minimum that we need is we have the valid copy, like we need a mechanism to have the valid copy. And if we don't have it, then we need to be in what we call an invalidate state. Yes, sir. The you mean the snooping logic where it's located? Is that your question? Where is what? Yeah, so the question is where is the snooping logic implemented? So the snooping logic is kind of like is able to read these and it's able to read this. So it's part of this the system that way. So usually on the memory controller. Okay. Another question? Okay. So this is called an MI protocol, a modified and invalidate. So modified means that I have the copy and it's a modified version that has the dirty bits equal to 1. And I means that I don't have this copy. It's invalidated. So either I had it, but it's invalidated, or I never had it in my cache. Okay? So for MI coherence protocol, if I have, let's say, 3 different cores, okay, and let's say I'm showing you just one line, okay, all the same addresses. Let's say all of them are address Z, okay. So let's say I have a sequence like this. That I have read one, I have a sequence like this. I have read one, then I have write 2, then I have read 3, and then I have read 1. So what it means here is that core number 1 reads, core number 2 writes, core number 3 reads, core number 1 reads. So the sequence I'm showing, like the syntax I'm showing it is this. All of them for the same address, okay? And initially, let's say all of them are in the invalidate state, okay? So as I said, each line will have a bit that shows its states. If it's like we only have M and I, you can think about I is 0 and M is 1. So when I say address 0 is in I state, it means that that flag is equal to 0. When it's in M state, that flag is equal to 1. Later, we're going to introduce S and F and so on. So we need more bits. Okay. So initially, all of these guys are in I state. Okay. Now, read 1 means that core number 1 wants to read. Okay. Since I only have M and I, that means that core number 1 will go to the M. It's a little bit counterintuitive because we're not modifying, we're just reading. But since I only have invalidate and M, I can only go to M. So I go to M, all these other guys stays in I because they're all still invalidated, okay? Now we go to this stage and write 2 happens. So core number 2 wants to write. Remember, when I want to write, I need to announce it, so everybody has to invalidate. So what will happen is that core number 1 will invalidate, and now core number 2 go to the M stage, and core number 3 stays in the I stage, okay? So that will happen when you have something like this, okay? Now read 3 happens, and what will happen here is that 3 needs to read it. It will announce that I want to read it. And what is important is that once I announce that I want to read it, all the cores needs to look at their local copy and see if they have the dirty bit there. It needs to write it back to the memory. So core number 2 will invalidate itself by, as a process of invalidation, it also writes back its data. Usually the notation that we use in this class is some form of a star here to indicate that write back happens at this state. I3 go to M and I1 goes to I, okay? So this will be what happens here. And finally, if R1 wants to read, again, R1 will go to M. This one is in I. And as I said, M has to be exclusive. We cannot have two cores in M state. As a result, I needs to actually go to, 3 needs to go to the I. So because at any given point, only one of them should be in the modified state. And that's a different definition of the protocol. So this will be what happens in this system, okay? Any questions about the protocol? Yeah. Which one? You mean the third? We are talking about this R3, right? So 2 is in M state and 3 is in I state, and 3 needs to read it. It cannot stay in the invalidate. It has to go to the M. Okay, when we are reading or writing, doesn't matter. We always go to the M because I want to grab this line from the memory. Okay, yeah.
Like why?
So that's actually like the segue to why we need more states, because of exactly this problem. That when we are reading, it's very unintuitive to go to the modified state and invalidate the other line, because all of them can live together, right? Because if I only want to read, I have just a clean copy from the memory. So, but in the MI protocol, which is the simplest protocol, I only have modified and invalidate. I don't have any other state. Once we're going to introduce what we call an S state or shared states, you're going to see that that's actually fixed this problem. Asterisk means that I do a write back. So at this stage, since I have the dirty copy, I write back. For example, here I don't have the dirty copy because I just read, so I don't need to write back. But here I have the dirty copy, so I write back. Okay? So as you see, this is working very well, but it's not the most optimized thing because it's just doing some unnecessary invalidation that we could have prevented. And the reason that we want to prevent this unnecessary things is that any broadcast is a traffic that we are adding to the memory subsystem. And there is so much traffic that we can introduce. More traffic means that we cannot use that bandwidth to actually bring useful data. So you want a coherence protocol that minimizes the number of broadcasts. So if you can somehow minimize the number of broadcasts and back and forth and reading from the main memory, we will do that. And that's actually the motivation behind introducing other ways improvement for cache coherency. The first one that we are introducing is a shared state. So we had MI protocol. Now we call it MSI protocol. So shared state is when we have clean copies, but multiple cores have that clean copy. Okay? So essentially we have now shared, modified, and invalidated. Okay? So let me actually show you an example that we had before, this time with, so read 1, W2, read 3, read 1. Okay? So initially all of them are in invalid state. Then core number 1 wants to read, and since he's reading and it's not trying to modifying the cache, instead of going to the M state, it goes to the S state. Okay? So it goes to the S. These one stays in the I. So S basically just say that it's a shared copy. It's not been modified. It's just a shared copy. Now, then W2 happens. And W2, since it needs to write, it needs to invalidate everything. So I1 goes back to I. This one goes to M. This one stays in I. Then R3 happens, okay? R3 wants to read it. So this one, since it wants to read it, goes to S. And as we said before, since this one has the dirty copy, it needs to write it back. So it writes it back to the memory and then core 3 reads it. But since now both of them have the updated copy, core number 2 no longer needs to invalidate itself. It just goes to the S state. So it goes to the S state. And then R1 comes, and again, since R1 just wants to read, this one also goes to the S state afterwards. Sorry, this one is I, and then this is S, and this is S, okay? So this will be what happens in this sequence here, okay? For example, here, if it has something like this, then the states would have been I. Then this one reads, this would be S, I. And then this one reads, this would be S, I, S, and so on and so forth. Okay? So the difference here is that if I want to read, I don't need to go to the modified stage. I reserve the modified stage only for writes, and clean copies always go to the S. Yes? Again, the purpose is if I want to just read, if I only have M and I, M was for both writing and reading, versus in some cases, so for example here, like for example here, sorry, actually here, in this case, that read 3 happens and read goes to M, right? And now read 1 happens, and now read 3 needs to invalidate itself because only one core can be in the M state. So read 3 invalidates itself and go to I, and then core number 1 goes to M. Okay, so there is an unnecessary invalidation for R3 here. R3 could just go to S state, to the shared state. I1 also can go to this shared state, and both of them can be in the shared state. The nice thing about that would be the next time R3 happens, I have the correct copy, so it would be a cache hit. It wouldn't be a cache miss. And also I saved one extra broadcast that was unnecessary. So for performance reasons, we do that. First that question and then yours. That's a great question. The question is then, when we are going from S to I, do I need to broadcast this to everyone or not? For now, we do broadcast from going to S to I. Later, we're going to have a state called E, exclusive, that when we are invalidating, we don't broadcast. But whether or not we broadcast really depends on the implementation. We necessarily don't need to broadcast invalidate when we are going from S to I. That is true. Yeah. Why do we need to specify write back? We need to also, yeah, we do that. So here there is a write back here. Or I mean, not sure which. I think we are using it. I don't remember the term, the syntax we are using, but we either put the write back there or on us. So it happens during this process of going from M to S. Any other questions? Okay, so as I said, S removes the unnecessary invalidation when we have 2 lines that just wants to read the cache, right? So R1 and R3, if both of them wants to read the cache, both of them go to S without invalidating each other's, okay? And S means that everybody has the fresh shared copy of the memory. M means that I have a dirty modified version of the copy. And I means that I don't have the copy. So for MSI protocol, this is what we have, okay? And again, the dirty line may or may not be present. So if we use a write-through strategy, there is no dirty line. There is no writing back. We always write to the memory. Only if we have a write back strategy, that's when we have the dirty lines and we need to identify the write back, okay? Keep that in mind as well, okay? This is also the state machine of this that you can refer to. That if anyone, so basically what I showed here is like clearly shown here as well. Take a look at it and let me know if you have any questions, okay? So now we know this. Then the final steps of coherency is further optimizing MSI. Next lecture, I'm going to show you 3 new states called exclusive or E, forwarding or F, and ownership or O. So we're going to add these 3 to our MSI protocol. So we're going to create MESI, MESIF, MOSI, and finally, all of them together will be MOESIF, okay? Which will have all these states. So we're going to explain why we need an E and an F and an O, and then we're going to explain the differences between them, and that will be the story of cache coherence. All right? Have a happy Thanksgiving and see you guys next week.